Now we have one last application or use of the determinant, and in order to illustrate this use, we need to define one more operation that is associated with a square matrix, and it's called the adjoint of a matrix, right? So we've seen, so given an n by n matrix, let's call it A, right? That matrix has cofactors associated with each entry, right? So given an n by n matrix, each entry right has an associated cofactor. That's the Cij, right? So an associated cofactor, Cij. Well, it turns out, and each cofactor is a number. So you can actually form a new matrix where you replace the entries of the original matrix with the corresponding cofactor, right? And that matrix is called the matrix of cofactors, right? So if we replace each Aij with the corresponding cofactor Cij, we form what is called the matrix of cofactors. Right? And that in itself is important, but it turns out the transpose of this matrix of cofactors is what we really need to get to. And that's what we define as the adjoint of a matrix. So the transpose of the matrix of cofactors right, is called the adjoint of A, right? So let me just kind of write it down symbolically. So we denote the adjoint by ADJ, right? And then you put your original matrix A in parentheses. So this means, or this is read, the adjoint of A, and then this is how it's defined. We form another matrix, and what we do is we replace the Aij's with the Cij, so that's that, and then we have to take the transpose of that particular matrix, right? And that's what we call the adjoint, right? Let's illustrate finding the adjoint. Let's try to see if we can do it for a 2 by 2, right? So just to kind of illustrate this, we'll start with the 2 by 2 since it won't be too tedious. So let's use our A as the generic A, B, C, D, right? And so this matrix has 4 cofactors, the C11, C12, C21, and C22. So let's find all of those. So C11 is -1 to the second power times the determinant of the submatrix that's formed if I delete the first row, first column. But if I do that, all I'm left with is D, right? Now, again, remember, the bars here don't mean absolute value, they mean determinant. And the way we define the determinant of a 1 by 1 matrix, it's simply whatever that entry is. So it's just D, right? Again, of course, it's times the +1. So then let's write down the C12 cofactor. So that's going to be negative 1 to the third power. Now delete the first row, second column. That leaves me with just a C. Right? So again, this is the determinant of this C, which is just the C, but then it's times negative 1. So we have a negative C there. Right? And then C13, not 1, 3, there's no third column. C21 is negative 1, again to the third power. And now delete the second row, first column. So second row, first column, that just leaves B. So you have your B there. And again, the determinant of a 1 by 1 matrix is just that entry. And then it's times negative 1. So the C21 cofactor is negative B. And then finally C22, that's negative 1 to the fourth power. And delete the second row, second column, so we're just left with an A, and that's times a positive 1, so that's just an A. All right. So let's write down now the matrix of cofactors. That doesn't really have a nice like notation to it, so I'm just going to write down this is the matrix of cofactors for this 2 by 2. So the matrix of cofactors, and it says where you simply replace each entry with its cofactor. So replace the A with the D, the B with the negative C, the C with the negative B, and then the D with the A. So right here, right? And then when you take the transpose of this is where we get the adjoint. So the transpose of this, so the adjoint of our original 2 by 2 matrix is the transpose of this. So it's the transpose. Let me put the transpose symbol there. And then when we take the transpose, that row becomes that column. So the first row becomes the first column like that. Second row becomes the second column like this. And there we go. Right? And I want you to take a look at the original matrix and its adjoint. This might look familiar to you. This is that trick that we do, or in fact, it wasn't really a trick. After we did the Gauss-Jordan elimination and we did our process for finding the inverse of a 2 by 2 matrix, this was the form that we saw, and then of course it was times 1 over the determinant. So this is that same matrix that that where we do that kind of switch thing, where we switch the A and the D. So that's what happens here, and then we change the sign of the entries on the main diagonal. So what we've been doing all along, when using that formula for finding the inverse of a 2 by 2 matrix, we were actually making use of this adjoint. We just didn't call it that way. Why didn't we call it that way? Well, we didn't know what a cofactor was, right? We didn't know what a cofactor was, so we couldn't have defined the adjoint until we knew what a cofactor was, right? So what this means is, so then it shows that A inverse, right, for the 2 by 2 matrix, this formula that we've been using. So again, this is how we used to write it. The AD minus BC, and then we just kind of, we wrote down what the formula was telling us to do, but we didn't have names for everything. But now we have a name for this AD minus BC. That's the determinant of the matrix. So it's really this. And now we have a name for this thing. It's really the adjoint of the matrix, ADJ of A. And it turns out that this formula holds not only for 2 by 2, but for every n by n invertible matrix, right? So let's actually state that as a theorem. I'm not going to give the general proof, but again, what I've been trying to do, and hopefully you got a sense of it, is I'm trying to establish a lot of these results for the 2 by 2 matrix, and then just kind of extend it, either give some kind of intuitive argument, or basically just say that this process holds not just for 2 by 2, but for n by n, right? So here is our theorem, right? And this basically is a theorem that now gives us a specific formula for the inverse, right? Again, not necessarily a process, but a formula, and there's a difference between those, right? So it says if A is an n by n invertible matrix, then we now have a specific formula for its inverse. So then A inverse is equal to 1 over the determinant of the matrix, right? And now we have lots of ways for finding the determinant of a matrix, and times the adjoint of that matrix, right? Times the adjoint of A. So this is really the new piece now, and it all comes together: inverses, determinants, and then this new concept that we're calling the adjoint. All right. So just to kind of wrap this up, I mean, there's not much else to do other than to illustrate maybe how this process works. So let's do it for a 3 by 3. For a 3 by 3, it's not necessarily an easy process, because you have to find all the cofactors, right? You have to find all the cofactors, then form the adjoint, and then since you have the cofactors, you might as well use a cofactor expansion to find the determinant. And if that determinant is not equal to 0, right, which will guarantee this, then we can go ahead and use this formula to find the inverse. So let's illustrate it with a 3 by 3 example, right? So let's say this is matrix A, and we have 2, 1, -1, 0, 0. I won't make it triangular. I mean, I could make it triangular, but let's make it like non-triangular, something like this. So here's our matrix, right? And let's first find the adjoint. Since that's the new thing, let's find our adjoint, which means I have to find all 9 cofactors. So if you remember, that was a process that we did way, way back, and it was pretty tedious, but let's go through it. So C11, that's -1 squared times the minor of 1, 1, 1, 3. So that ends up being, let's see, we got 3 minus 1, so that's 2. And then C12, that's -1 to the 3rd power, times the C12 minor is 0, 1, 0, 3. So that cofactor is going to be 0 for sure, because you have 0 minus 0. And then C13, that's -1 to the 4th power, times that minor, so 0, 1, 0, 1. So 0, 1, 0, 1. And that again is 0. Okay, 0 minus 0. So that cofactor is 0. Now let's go to the second row. So we got to find C21. So that's -1 to the 3rd power Now block out the second row, first column. Then we're left with 1, -1, 1, 3. That is the negative of 3 plus 1. So -4. Let's do our C2, 2. Block out the second column, second row, so we're left with -1 to the 4th power times that minor, which is 2, -1, 0, 3. So we end up with 6 minus 0 times a positive 1, so that's 6. C2, 3 is -1 to the 5th power. Again, block out the now second row, third column, so you're left with 2, 1, 0, 1. So that's 2 minus 0. Don't forget there's a -1 in front of that, so -2. Alright, well, we're 2/3 of the way done. We got 3 more cofactors to go. So C3, 1 is -1 to the 4th power times. Now, remove the third row first column, so I'm left with 1, -1, 1, 1. So we have 1 minus -1, so that's 2. Now the C3, 2, that's -1 to the 5th power. And what do we end up with? So remove the third row second column. So we're left with 2, -1, and then 0, 1. So we have 2 minus 0, but then there's a -1 in front of that, so that cofactor is -2. And then our last cofactor, C3, 3, that's -1 to the 6th power. And then we can block out the third row, third column, so we're left with 2, 1, 0, 1. And that cofactor is equal to 2. All right. Okay, so we got all 9 cofactors. So the adjoint of the matrix, so let's scroll down. So our adjoint of our original matrix form the matrix with these 9 entries in the order, which is why I did them in that particular order. So it's going to be 2, 0, 0, -4, 6, -2, and then 2, -2, 2. But it's not just that. We then have to take the transpose of it, right? So in the square brackets would be the matrix of cofactors, and then when you take the transpose of that matrix of cofactors, that's what gives you the adjoint, right? And it's another matrix. So it's the matrix 2, 0, 0, -4, 6, -2, and then 2, -2, 2, right? So that's the adjoint. All right, so we have, I would say, more than half of what we need to find out if this matrix, or to be able to write down the inverse of this matrix. But in order to do that, I need the other piece, which is the determinant, right? So for the determinant, in fact, let me go back up and just show the original matrix, right? So if I wanted to find the determinant here, remember I can use any row or column for my cofactor expansion. I look at this and I see the zeros in this first column, and I already have the cofactors here. So all I have to do, so the determinant of this matrix, right, is going to be like the A11 times C11. But then if I use these remaining entries in the first column, then because these A values are 0, then I would be adding 0 to the rest of my expansion. So it really just boils down to 2, which is this number, times this cofactor, which is also 2. So my determinant is 4. And that's a good thing, because since my determinant is not 0, it tells me that this matrix has an inverse, right? So we have a determinant of 4. Matrix has an inverse. Well, what is the inverse? And this is where we can use the adjoint. So it turns out that the inverse of my matrix, let me write down the formula. So it's 1 over the determinant of the matrix times its adjoint. We just found that its determinant is 4. So this is 1/4. And then times the adjoint, which is right here. So the 2, -4, 2, 0, 6, -2, 0, -2, 2. Distribute the 1/4, and we have our inverse. So it ends up being 1/2, -1, 1/2, and then 0, 3/2, -1/2, 0, -1/2, and 1/2, right? So this is a completely different way, right? No Gauss-Jordan, but we're able to find the adjoint, the inverse, by finding the adjoint and multiplying by the reciprocal of the determinant. Right? And that wraps up our look and use of determinants. I hope you found them interesting. They certainly keep us busy with all the arithmetic computations. But as far as what they enable us to do, they've now given us alternatives to, for one, solving a linear system that has a unique solution, and two, finding the inverse of an invertible matrix. Two of the big processes as far as linear algebra is concerned. See you in the next video.